Hi everyone. So today's lesson is on 3.9, which is graphing sine and cosine functions with their transformations. Leading into this lesson, it's really important that you make sure you do the investigation before, where you're looking with Desmos at different sliders for the different pieces of the transformations. It's going to make this go a lot easier. So first we're going to start by just reviewing our parent functions for sine and cosine. Remember that the parent functions are coming directly from graphing the terminal points on the unit circle, and our sine function corresponds to those y values. So remember, when I'm at theta is 0, sine is 0. At pi over 2, sine is 1. At pi, sine goes back to 0. Sine of 3 pi over 2 is negative 1. And then sine of 2 pi is 0. So this is one trip around the unit circle. And then as I go around the unit circle again from 2 pi to 4 pi, the cycle is going to repeat. So we get this sinusoidal or periodic movement. If I'm going to negative pi over 2, sine of negative pi over 2 is negative 1, and sine of negative pi is 0. So we know again that this continues over and over and over. It repeats every 2 pi units. So then let's talk about the domain and the range. So my domain is all real numbers. I can plug in any angle measure and I'm going to be able to get one y value. So for every I'm sorry, I'm all mixed up. My domain is all real numbers because I can plug in any angle I want and I'm going to get an evaluation back. Now the range is from negative 1 to 1. So if I plug in any angle measure, the only outputs that I'm going to get back lie between negative 1 and 1, and I can see that in this graph here. The amplitude is 1. Remember, we defined the amplitude to be the height of this wave from its midline or its equilibrium. And then the period is 2 pi. And we defined the period to be the length of one cycle. So if I'm looking at just one cycle before it starts to repeat itself, you need a full 2 pi units. Now the x-intercepts, we wrote those as x is equal to k pi, where k is an integer. Some of you opt to use this notation here where you say k is an element of the set of integers, and that is amazing. So that is a review of our parent function of sine. Now what I'd like to do is I would like to review cosine. So cosine is the x values on this unit circle, so I'm underlining them there in yellow. So cosine of 0 is 1, cosine of pi over 2 is 0, cosine of pi is negative 1, cosine of 3 pi over 2 is 0, and cosine of 2 pi goes back to 1. So this is one cycle or one trip around the unit circle, and then the cycle will repeat itself as I go from 2 pi to 4 pi. So I'm going here, I'm just going to follow my pattern. Make sure I put some arrows on the ends because the cycle will repeat itself over and over and over. And again, it's also going to repeat every 2 pi units. The domain is all real numbers. The range is negative 1 to 1. The amplitude is 1. And the period is 2 pi. Notice they are the same, sine and cosine. However, the x-intercepts are different. If I'm looking at the x-intercepts of cosine, they're occurring at pi over 2, 3 pi over 2, 5 pi over 2. So I'm going to write that x is equal to k pi over 2, where k is not just an integer, but it is an odd integer. It can be even. In just a quick example, if you were to allow odd integers, like 4 per se for k, you would have 4 pi over 2. That would simplify to 2 pi, and you notice that 2 pi is not an x-intercept. So I can't have any even number here. I have to make sure all my integers here are odd. So that's a review of your parent functions. And now let's review the transformations you saw in the activity yesterday. So for the A, whenever we looked at that slider for A, we saw that the A changed the amplitude, and it was specific. Whatever the A value was, that was the amplitude of my graph. So A is going to be equal to the amplitude. Now B changed the period. So we saw that. We saw with bigger V values that I had more waves, so more showed up. And with a smaller B value, it got really, really long and it stretched it out. So the B changes the period. We also notice that whatever B is, B tells us the number of waves that occur every 2 pi units. So if you had a B value of 2, that meant you needed 2 waves for every 2 pi units. If the B was 3, you needed 3 waves from 0 to 2 pi. If you had B as 4, you needed 4 waves. And we also saw where B was a half, and you saw that it stretched out and you only had half a wave from 0 to 2 pi. We also discovered that the period of the function is going to be equal to 2 pi divided by whatever that B value is. So picture your original wave from 0 to 2 pi, and you need to fit B waves into that window. So if I need B waves, I'm going to divide 2 pi into B equal parts, and that will give me the length of 1 wave, which is the period. Now C we saw was a horizontal shift. And we said if C was greater than 0, it moved to the right. And when C was less than 0, it moves to the left. Now, often, this is not called a horizontal shift. It's called a phase shift when I'm dealing with these periodic functions. And D was a vertical shift. When D was greater than 0, the function moved up D units. And when D was less than 0, it moved down D units. And with these periodic functions, we usually don't call it a vertical shift. We usually call it a vertical displacement. So what I would like to do first is I'm going to write a function here. Let's say we have f of theta equals 6 sine of 3 theta minus a 6. So what I want to do is I just want to go through and outline the transformations that are going to occur to the sine function. I notice here that my a value is 6, my v value is 3, I have no c value, my c value is 0, and my d value is a negative 6. So what this tells me is that my amplitude is going to change. It will now be 6. With this b value of 3, that means I need to fit 3 waves from 0 to 2 pi. So my new period is going to be equal to 2 pi divided by 3. And then this last piece tells me that I need to do a vertical displacement down 6 units. Let's look at another example. Let's say I have f of theta equals 2 cosine of 6, let's do a 6 theta plus pi. I kind of want to rewrite this because that's confusing. Let's rewrite that 6 theta. Let's see if I can get this in the same window as my original. There we go, right there. So you can see here that my a value is 2, my b value is 6, And it looks like my C value is a negative pi. But when I take a look up here, it's really important that you notice in here that B value is always factored out from the independent variable. So I need to pull out that 6 in order to see the true horizontal shift. So when I'm looking, oops, let me go, there we go. So when I'm looking on the inside, let's factor out that 6. I'm afraid I'm gonna run out of space. So let's move down here. So 2 cosine of 6, and then let's have some inner parentheses. That way I don't run out of space. Okay, well, let me erase that. So we're kind of stuck with it, no worries. So 6 times what will give me a 6 theta, and that's a theta. And then 6 times what will give me a pi, and that's pi over a 6, because 6 times pi over 6 is equal to pi. So now I can see that my B value, which is still 6, I can see that in the first iteration, and I can see it here in the second iteration. And now I can see the true C value, that C is going to be equal to negative pi over 6. And remember, it's negative because my general form that negative is built in. So I need the C to be negative in order to have a minus and negative become a positive. So let's go through all the transformations that are happening here. This 2 is changing my amplitude to 2. This 6 right here is changing the period to 2 pi over a 6. And 2 pi over 6 is equal to pi over 3. Oh, need a 3 there. Pi over 3. So this is my new period. Amplitude is 2. And now I can see with this C value right here, I'm moving to the right. No, I'm moving to the left. Pi over 6 units. Moving to the left because my C value is negative. So moving to the left, pi over 6 units. So it's really important that if you have a B value and a phase shift, that you make sure you factor out that B value to see what the C value is. So now what I want to do is I look at what negatives do. So using what you know about transformations of functions, how do you think the following functions are related to the parent? So in this first example, I've got sine already graphed, and I want to look at negative sine of x first. Well, I know whenever I have a negative out front, it changes my y values to negatives and negates their sign. It's a reflection about the x-axis. So when I reflect the x-axis, all my 1's become negative 1. All my negative 1's become positive 1. So there you can see that reflection. It kind of looks like DNA strands when I look at both of them together. So that would be negative sine of x. Now let's look at the negative on the inside. Based on what we know about transformations, this is a reflection about the y-axis. So that would take all of the x values and make them negative. So let's just take a look at the parent function from 0 to 2 pi. If I were to take that and reflect it about the y-axis, it would map right here. If I were to take the red from 0 to 2 pi and reflect it, it would land on the green. Now if I take the red from negative 2 pi to 0 and I reflect that about the y-axis, it would land here. So we should notice that these, for the sine function, these produce the same result. And indeed, what we've just discovered is that negative sine of x is equal to sine of negative x. And this is an identity that'll likely be discussed later. And it also tells us that sine is an odd function. And you guys have learned about even and odd functions back in Algebra 2. Now let's look to cosine and see if it behaves in the same way. So first, let's do the reflection about the x-axis. When I reflect about the x-axis, just looking from 0 to 2 pi, I get this movement. Now I can keep going from 0 to negative 2 pi. Notice the x-intercepts don't change at all, but all my positives become negative and all my negatives become positive. So there's that reflection about the x-axis. Now in sine, we saw that when I reflected about the y-axis, it was the same graph. Let's see if that happens with cosine. Now if I take my cosine function, I'm going to look from 0 to 2 pi, that piece right there, and I'm going to reflect it about the y-axis. What happens is it maps here, not onto negative cosine of x, but onto itself. Now, if I were to take the left part from negative 2 pi to 0 and reflect that about the y-axis, it reflects here. So what I see is not that cosine of negative x is equal to negative cosine of x. What I see is that cosine of negative x is just equal to cosine of x, to the original. So when you reflect cosine about the y-axis, there's actually no change, and I can, in the graph, and I can just pull that negative out and basically pretend like it doesn't exist, that there is no transformation. This is another identity that you might discuss in pre-calculus or later on in this course. And this means that cosine is an even function, similar to like y equals x squared, which we learned about in Algebra 2. So now that we have all of the transformations complete, it's time to start working on some examples. So what I want to do first is take a look at this example, identify the parent function. I can see that the parent function is sine of theta right here. And I've got two transformations occurring to it. First, I have this 3 out front that's changing the amplitude. So my new amplitude is going to be 3. And then I have minus 2 in the back, that's a d value. So I'm going to have a vertical displacement down 2. So I'm always going to start with my parent function, and I'm going to color code it based on the colors that I put up here. So my parent function for sine, start at 0. At pi over 2, I'm at 1. Pi, I'm at 0. 3 pi over 2, I'm at negative 1. And at 2 pi, I'm at 0. So I'm going to carry this through. There's the parent function. Now I need to change the amplitude to 3. So when I do that, my x-intercepts don't change, but instead of going up to 1, I'm going to go up to 3. And then negative 1 moves to negative 3. So I can see the size of the wave getting bigger. So this in blue, this would be the graph y equals 3 times sine of theta. In green is just y equals sine of theta. And now my last step, down 2. If I were to move my blue graph down 2 units, every single point, I'll get my final graph. Need one more point. There we go. And so there's the final in the yellow. Y equals 3 sine of theta minus a 2. Now let's go through and look at the properties. The domain of the function is all real numbers. The range is from -5 to 1. Notice the range started from -1 to 1. The amplitude changed it from -3 to 3. And then when I shifted down 2 units, it moved to -5 to 1. The phase shift, there was none. The amplitude is 3. There wasn't a period change, so the period is still 2 pi. And my vertical displacement is down 2 units, or you're welcome to write -2. So there's my first example. Let's look at the next one. Left to right. Oops. So here I'm asked to graph the function g of theta equals -2 cosine of theta plus 3 pi over 2. So I've got a couple of things going on. First, I have a reflection about the x-axis with the negative out front. I've got an amplitude change to 2. And then I have a phase shift to the left 3 pi over 2 units. And of course, my parent function is cosine. So let's start by graphing my cosine function. We haven't really discussed order of transformations, but it's similar to how we did transformations of functions. We are going to do any reflections we have first. Then what we're going to do is we're going to do transformation. Wrong slide, there we go. So reflections first, and then I'm just going to go from left to right. So now let's take care of that reflection about the x-axis. Now this one has several iterations, so I might delete or erase some of my transformations as I go, depending on how messy this gets. So right now I've got y, or I guess I should say g of theta equals cosine of theta in the black. Then I have g of theta equals negative cosine of theta in the red. And moving on to blue and changing that amplitude. Now I need to change the amplitude to 2. So instead of going from -1 to 1, I am now going to go from -2 to +2. And I'm from my red. So there is the blue. And now I only have one more transformation. Let's make sure we get this. This is -2 cosine of theta. I need to erase this 2 right here. The red is just negative cosine of theta. The red's just negative cosine of theta. The blue is -2 cosine of theta. So now what I'm going to do is I need to shift to the left 3 pi over 2 units. So what I'm going to do first is I am going to go through and I'm going to delete or erase everything but the blue. Oh, I'm not going to be able to get rid of part of that black because I changed the slide in the middle. But I can get rid of this. A decent amount of this I can get rid of. All right, so that's all I can get rid of, but that'll at least clean this up so I can look at the blue. Now, what I like to do when I'm doing a horizontal shift is I like to start at 0 and just take it point by point. So I'm going to look at this point. I'm going to move it to the left 3 pi over 2 units, which will move that point here. Now I'm going to look at the next point I have, and I'm going to move it to the left 3 pi over 2 units, which will move it here. So I'm taking this piece, and I've moved it over to the left 3 pi over 2 units. Now let's take a look at this point. When I move it to the left 3 pi over 2 units, here it lands. So now I have this curve move to the left 3 pi over 2 units. And from there, I'm pretty set to go ahead and follow my pattern. I know from 2, it's going to go to 0. From there, it will move to negative 2. From there to 0, back up to 2, and back down to 0. So my green is my final. I'm going to erase everything that it allows me to other than my final answer. So there is the final in the green. Just ignore the little traces of the parent function that are still left over. G of theta equals negative 2 cosine of theta plus 3 pi over 2. And now let's fill in the desired information. My domain is still all real numbers. My range is from negative 2 to 2. It got changed with the amplitude. I had a phase shift to the left 3 pi over 2 units, or minus 3 pi over 2. My amplitude is 2. My period is still 2 pi. And no vertical displacements for this example. All right, let's take a look at the next. Here I have f of theta is equal to sine of 2 theta. So here I can see my parent function is sine. And the only change I'm going to have is coming from this b value, which is a change in the period. So I'm going to have a new period, and it's 2 pi over the b value, which is 2. So my new period is going to be pi. I can go ahead and write that down here. This also means that I need 2 waves to occur from 0 to 2 pi. So let's start by graphing out the parent function. I've got 0. Oh, I can do my points here. 0, 1, 0, negative 1, 0. And then go from negative 2 to 0. All right, so here's my sine function, my original. Now what I need to do is I need the wave that's occurring from 0 to 2 pi, I need to shrink it down so that it ends here at pi. I need to have one wave from 0 to pi and another wave from pi to 2 pi. So what I'm going to do is I'm going to look at these 2 notches right here, which are pi over 4 and 3 pi over 4. And what that is going to allow me to do is give me equal distance. So that I start at 0, I'm going up to 1, back to 0, down to negative 1, and back to 0. So I'm going through the unit circle, but now I'm doing it from 0 to pi. And now I can see that's one period, one wave, and now I have the information that I need to get from pi to 2 pi. So I really just needed new little hash marks in order to achieve my goal. So let's continue this. Let's go halfway between these old hash marks to get one more wave. And then from negative pi to negative 2 pi, I need another wave. So there is my final in the red. So the domain of my function hasn't changed. The range is still from negative 1 to 1. There were no phase shifts or vertical displacements here. And my amplitude is still 1. The only thing that has changed is the period is now pi. What I'd like you to do is think about, let's still do sine. What do you think the graph y equals sine of 3x would look like? So think about, we did this in the investigation with sine and cosine. So let's take a look at this. 3. It's a b value, so I know it's changing the period. The new period is going to be 2 pi over 3. So think about that on like my unit circle from 0 to 2 pi. 2 pi over 3 is here. So you're going to have one wave from 0 to 2 pi over 3. Then your next wave is going to occur from 2 pi over 3 down to 4 pi over 3. And your final wave is going to occur from 0 to 2 pi or 6 pi over 3, which is 2 pi. So there you can see how that interval from 0 to 2 pi is going to be split into 3 equal pieces. So what you have, I'm only going to go from 0 to 2 pi. Here's my traditional pi over 2, pi, 3 pi over 2, and 2 pi. So this is my parent function. So now what I see happening is I'm going to have one of my cycles ending at 2 pi over 3, which is here. My second cycle is going to end at 4 pi over 3, which is here. And my last cycle will end at 2 pi over 3. So when I draw this, it's going to go, if this was split into 4 hash marks, because that's what I need, 1, 2, 3, 4, then I would have 1, let's see, 5 pi over 6 would be the next one here, pi, 7 pi over 6, 4 pi over 3, then 3 pi over 2, 5 pi over 3, 11 pi over 6, there they are. So every single notch is pi over 6 units. There we are. 1 cycle, 2 cycles, final cycle. There we go. And my negative 1 there is much lower than my 1. But there you can see the graph y equals sine of 3x and how you can split your period up. So my period is 2 pi over 3 and how that works. Okay, so now in this next example, we're looking at g of theta is equal to 4 times cosine of theta plus pi plus a 2. So there's a lot going on here. I can see that my parent function is cosine. This 4 tells me I'm going to have an amplitude change by 4. Here, when I have that theta plus pi, that means I'm going to be shifting to the left pi units. And my last transformation is going to be going up 2. So at this point, if you're feeling comfortable with the amplitude change, I would say go ahead and start thinking about, but instead of graphing the parent function first, I would go ahead and graph 4 cosine of theta. So I would go ahead and make that amplitude 4. If this is like throwing you for a loop, then graph the parent function first and then do the amplitude change. Okay, so this right here in the red, that's g of theta equals 4 cosine of theta. So it's the parent function of cosine with that amplitude change. Next, I need to shift to the left pi units. So I like to start here at 0, and I'm going to take this point, and I'm going to shift it to the left pi units. And then I'm going to go ahead and erase that. Next, I'm going to get my next point here, shift it to the left pi units. So it's moving from here to here. This one moved here to here. This one's moving from here over here. And then my third point, before I'll see a pattern, I'm going to take this next point, I'm going to move it to the left pi units. So I can see this piece move to the left pi units is right here. And once I have those three, I'm going to be able to follow the pattern. So I'm going to get rid of this, and this, and this. Grab my blue pen, and I'm going to be able to follow the pattern. So from here, -4, I go back to 0. Then I'll go up to 4, back to 0, down to -4. Then moving in the other direction, I go down to 0, down to -4, and then I'd pop back up. So there's several things I want you to notice. When we move to the left pi, I could have moved to the right pi. If you notice, if I took this point and I moved it to the right pi units, I would get the same thing. It would also be the same thing if I had a reflection about the x-axis. If I had moved this point down here, I'd have the same graph. So you're going to notice a lot of these in the transformations, that one transformation could be performed several ways to get you the same result. Or different transformations, I should say, will give you the same result. All right, so I'm getting rid of my previous iteration so that my graph doesn't look too jumbled. And I'm on to the last step. Now in the last step, I gotta go up 2. So I'm taking all of my points and I'm moving them up 2 units. Notice, this is going to change my midline, and the vertical displacement is the only transformation that's going to change your midline. Now my midline is at the horizontal line, y is equal to 2. So here in the green, that's going to be my final graph in the green. So the blue is the g of theta equals 4 cosine of theta plus pi. Green is the final graph. So looking at the final graph, I notice that the domain is still all real numbers. The range now goes from -2 and up to 6. The phase shift was left pi units. The vertical displacement was up 2 units. The period was not changed, it's still 2 pi. And the amplitude is 4. All right, I think I have one more example. All right, so in this, I automatically notice that I am going to have to factor out that 2 in here to see the true phase shift. So let's go ahead and do that first. I've got -2 times cosine of 2, that's my b value that needs to be pulled out, times some binomial here. So I know 2 times theta would give me the 2 theta, and then I would need to do 2 times pi over 2 to get to the pi. So just to reiterate, if I have 2 times theta plus pi over 2, and I distribute this, I would get 2 theta plus a pi, which is what I have here. So what this allows me to see is that I have several transformations going on. I can see my cosine function is my parent. I've got a reflection about the x-axis, an amplitude change of 2. I have a period change here, and then I also have a phase shift here. So this is a big one. So here what I suggest you do is either graph your parent function or the reflection of the parent function first. I'm going to graph the reflection of cosine of x first, since that's pretty easy. So instead of starting at 1, I'll start at -1. And then I've got 0, 1, 0 back to 0, and at -1. So I can go ahead here. So that's the graph of negative cosine of theta. Now what I need to do is I need to change the amplitude. So my negative ones will go down to 2, and my ones will go up to 2. And I mean my negative ones will go down to negative 2. So here I see that amplitude change. All right, so I'm going to erase my red graph now because it's time for the period change. So as I get rid of this red graph, think about what the new period is going to be. I know that that 2 means that I need 2 waves to occur from 0 to 2 pi units. So if I've got 2 waves that are occurring from 0 to 2 pi units, that means my new period is going to be pi. So here from negative 2 pi to 2 pi, where I now currently see 2 waves, I'm going to see 4 total waves. So it looks like I need my green pen, the way I've color-coded this. Now in order to shrink this down, I want this right here to be ending here. Here's my start, and here's my end, but I need 4 different notches. So I'm going to half here and here so that I now have new markers for where I'm going to 0, 2, 0, negative 2. So that gives me 1 wave. Now I'm going to half and half again, so I have 0, 2, 0, back to negative 2. So there's that period change. I need to do it on this side as well. And then one more time. So I could go ahead down here now and show that my period is pi, and I know this also from my formula, 2 pi over b, which is pi. I can also go ahead and say my amplitude is 2. So now what I'm going to do is I'm going to get rid of my blue graph. That was the negative 2 cosine graph. I'm going to keep, I need to get a little thicker. A thicker eraser would be super helpful, I think. Alright, but I'm kind of stuck with this small one. No worries. I've got one more transformation to go. I need to go to the left pi over 2 units. So it's important that you notice, because I've drawn these new notches in here, I have points every pi over 4 units, but I'm moving left pi over 2. So it's going to be every 2 of my smaller notches. So I'm going to start here, because I like to start at 0. I'm going to move this point left pi over 2 units. Now this next point, which is at pi over 4, I'm going to move it to the left pi over 2 units. It will land here at negative pi over 4. Next point here, I'm moving it to the left pi over 2 units. It's landing at 0. And now that I have that, I have my pattern. And I am all set. As I'm graphing this, it kind of looks, well, it does look like this moving to the left pi over 2 units for this graph would have been the same if I was reflecting this final green graph over the x-axis. Looking at the final green graph. Excellent. So now I'm going to go through and I am going to erase the green. Why am I the green, because the yellow is my final. That way it's clear what my final graph is. Alrighty. So the domain of my function is still all real numbers. The range is going from negative 2 to 2. There was a phase shift going to the left pi units, and there is no vertical displacements. And that was our last example. So now you guys are all set to do problem set 3.9 if you do more practice. and the solutions are also posted on the website.